it smooth, right? If the shape is not perfectly spherical, or if the bond is asymmetrical, then one particle will debond faster than the other, and the only way to move then is by dilation or by structural integrity crushing.
Okay.
And I'm not sure, so I think you simulated already the free dilation case, right?
Yeah, but after the last time meeting, I plan to reorganize the structure of the paper a little bit. So yes. maybe from this if you still remember, I have those this following cases, right? Mineral morphology, crystal integrity. So in the morphology, it's just the difference between the calcite, meteorite. Integrity is just like you said, generate a symmetrical. Like on the one side of the wedge, it has a more concentrated crystal, and on the other side, it has a little bit sparse or less particles wedge.
I would easily change the.
Yes. Yes, that is doable. Yes.
Upper bound you do is, let's say, a 10-degree cone angle, and at bottom you do a 15-degree cone angle.
Yes, exactly.
An asymmetrical wedge.
Yes. So the shape is not very regular. It will be kind of like a irregular, not symmetrical structure, right? So this is to test the integrity. And cohesion, of course, just give GC bond cohesion or not. And the frictional resistance, like you said, in the frictional resistance case, you can see if you are sharing on a very smooth case, but for the smooth case, if you want to see that tilt or the rotation of the wedge, should we limit the vertical displacement or free dilation of the whole screen?
Well, I think if you would suppress dilation,
I don't think you have.
It can only let's say if you have a very strong structural integrity of the crystal,
you
have an asymmetrical bond. So even then, it can only move horizontal if it can dilate, because it is bond within the structure, and so it's interlocked within the wedge.
So still restrain the vertical displacement. Yes.
So if you would restrain it, then I would say you can only break it by crushing the crystal or by overcoming the cumulative friction and cohesion at the bottom interface.
But if there's no friction, if you are dealing with a smooth...
If everything's smooth, it will just rotate.
Okay, I see.
And you would have no dilation because it's just horizontal movement and the wedge can rotate because it's a perfectly round and smooth surface.
Okay, and this file is just vertical displacement, and I have another, it's the confining pressure.
Asymmetrical wedge.
No, I mean for the case 4 is friction, and case 5 will be the vertical displacement constraint. Case 6 is based on our last time discussion at a constant confining pressure. So in this case 6, additional case 6, I will mention the interlocking using that equation from Taylor. To quantify that dilation, if you still remember the equation Julian provided, he mentioned that dy over dx, that ratio is how you quantify the effect of dilation, right?
Yeah.
So, but that can only happen under if you are under the case of the constant and under the existence of the confining pressure. If this is if you are free dilation, then you have a zero confining pressure, right? And if you are fixed restrained vertical, it's restrict vertical displacement is going to be the infinite confining pressure, right?
Yes.
So in case 6, in the case 6, this confining pressure case. So what I'm going to do is I'm going to free dilation, give like 100 kPa, 200 kPa constant pressure, and quantify the effect of dilatancy under a different confining pressure range.
Yes.
So if you think this makes sense, or...
Yes, so maybe I'm not sure how easy it is to get a sort of a constant vertical force.
Very easy in the DEM. Yeah.
Then you can do two or three levels of confinement to get a trend and to see how it goes from zero confinement, free dilation towards towards infinite confinement, and you can maybe plot a trend. Right?
Yes. I can also plot that vertical displacement as the function of the horizontal displacement, or the vertical force as a function of the horizontal displacement.
Or you can plot peak stress as a function of normal stress, or you can maybe plot what you also often see is the peak stress divided by the. So you can plot the peak stress divided by normal stress versus horizontal displacement.
Peak stress divided by the horizontal stress.
Sorry, the shear stress divided by the vertical stress.
Shear stress divided by the vertical. Why you normalized with the vertical?
To show that effective dilation is bigger at low stress levels.
At low stress. Okay, low stress. Is this this phenomenon has been observed in the MICP, like the particle element scale treatment? Like we have.
That's what I showed you on that graphel paper, right? That we did different tests at different vertical confinement, and we showed that the higher the stress, the more you suppress the dilation.
Yeah. Okay. I just want to make sure this observation is consistent with the previous.
Yes. So I think if you look in the literature, the higher the stress, the higher the confinement stress, the lower your dilation, because at some point stress is so much that you have to break the bond and you see zero dilation. But you have a higher peak stress.
Okay, I see. So in this case 6 constant confining pressure case, I will mention the word interlocking, but from case 1 to 5, I think based on Julian's expertise, those 5 cases has nothing to do with the interlocking. You are just breaking an obstacle.
No, wait, yes, no.
Because in these 5 cases, you are restricting the vertical displacement. I think this is his concern.
Yes, so there's no dilatancy there.
Yes.
The peak strength, correct. If you suppress full vertical displacement, but this is, why did we do this? Because the experiment was done in that way.
Yeah.
Right?
Yeah. And then we make another extension that if we release this vertical restraint and we apply confining pressure instead, then we can test the effect of interlocking. Which also reminds me that in my next element scale paper, which I plan to use Venice, that UCS data and some triaxial test data, I can use the word geometrical interlocking because in the element scale you always have the dilation, this confining pressure and the corresponding dilatancy. Yes. Yeah. So maybe if, for this paper I'll avoid using the word geometrical interlocking in the title or in the.
Yeah, not in the title, but interlocking is one of the phenomena.
Yeah, one of the phenomena.
Which generates strength, right?
Yes, I would say this is interlocking is the additional term because, I mean, for this paper itself per se, seems like if we don't forget all those words, those interlocking, this I feel it's just like you're breaking something very tough, very stiff, which because the wedge of that Cossack wedge has the same modulus or the stiffness with the silica sand, right? Almost, right? So if you are breaking so it's basically like you are breaking another sand particles that is perfectly embedded in here, right?
But then it's weaker than silica.
Yes, and assume those two different particles they don't have this or cohesion or maybe adhesion because there are two different materials. If there's no adhesive force, you can still break it. And macroscopic perspective, it just manifests as the shear strength enhancement. I think this is the core point we want to tell in this story.
Yeah, if I look at these 5 parameters, in fact, or 6, I only see 3. One is the mineral morphology/integrity, right? This is the CC bond, or the number of CC bonds. That's all in the first one. 3 and 4 is about the GC bond, right? And then 5 and 6 are all about confining stress or normal stress.
Okay.
And so then you break it back to, and so the overall strength will be a function of these three.
Yes.
It's the friction or cohesive force at the interface, which for glass beads, we can argue glass beads, number 3 and 4 are virtually zero, but number 1 and 2 are not zero.
Yes.
So, which means that, and then depending on 5 or 6, depending on the confining pressure, you will have dilation, because you still have structural integrity of the mineral.
Yes.
Even if you have no cohesion or friction. So then you have interlocking effect, which still generates strength. However, with glass beads perfectly round spheres, you may have zero dilation because you have free rotation. Right? If the wedge can rotate. But in fact, then I would say this is a special case for glass beads only, because they're perfectly spherical.
Yes.
And with perfectly spherical, zero cohesion, zero friction surfaces, it will rotate automatically with zero dilation, but you will also have zero strength. Right?
Yeah.
If you still have strength in glass beads, it must be because there is some 3 or 4, some cohesion or friction at the interface, and or that you have an asymmetrical crystal, so that the bottom surface is different than the top surface, which means that you may break one grain from the top if it's a smaller surface, but still you have a little bit of cohesion and friction at the bottom, which means it cannot rotate. It can only rotate if you break all the GC bonds at the base, or overcome the friction at the base, then it can rotate, or it can dilate. So those are the two pathways to failure. One is dilation out of the socket, the other one is rotation of the socket. So that is, and whether, depending which one occurs, depends on the vertical stress. Right? If there's infinite vertical stress, then obviously you have high friction at the surface, but also you will probably rotate the crystal if the crystal is strong enough that it won't break.
Yeah. Yes.
So then
Even more cases.
Say again?
Now in this way we have even more considerations for
No, it's less.
It's less?
So I bundle 1 and 2. This is all about the number of bonds and the individual bond strength. Those are 1. This is the mineral strength.
Should I merge 1 and 2 together? Maybe merge 1 and 2, combine 3 and 4, combine 5 and 6?
Correct.
Yes.
Yes.
Then I should think about another name of this. Or they are the sub cases.
Yeah, so both are subcases. It's 1A and 1B.
Okay.
So it's all about,
No, I'm just thinking from a reviewer's perspective. Like I don't want to make things a little bit complicated for the reviewers.
So one is all about the mineral strength, which is a function of the type of mineral.
Yes.
CC strength,
Yes.
And
Mineral itself, yes, mineral strength. Mineral strength depends on the morphology and the integrity.
Yes.
Yes. And second is the cohesion friction is
interface.
Interface property. Yes.
Yes.
Interface property.
And maybe that also involves shape then, right?
Yeah,
So
but for the
size of the interface.
size. So for the size of the interface, how do you propose to?
So I would just give an example. Now you have symmetrical.
Yes.
Right.
Symmetrical.
You can vary C and you can vary the friction angle. So those are two variables. And then you can have an asymmetrical, which is bottom bigger than top.
That is also very similar to the crystal integrity, right? If you have one side.
Yeah, crystal integrity now you have it random.
Random. Okay.
But in an asymmetrical wedge, it is not random. It's just bigger at the base and at the top, right? So, which means you enforce it to fail first at one surface, but then the strength then depends on the friction of the bottom surface or the dilation, which is a function of effective stress.
Okay. Okay, so 3, 4. I made another 5 as the. So 3, 4, 5 will be the. So this 5 will be the size of the size effect. So or asymmetrical, right?
Asymmetrical wedge shape. So that
Yes.
it may also be that in real life or in an element scale that the wedge is not perfectly between two particles, but it may be more on one
Yes.
particle, smaller on the side of the other particles.
Yes. And then the 6 and 7, I'll make another case. There, I will merge those two together. Maybe just interlocking.
Just the stress conditions.
Stress conditions. Stress conditions. Yes.
Yes.
Yeah, I think now it's more clear. Yes, stress conditions. Ooh.
So one is high stress, which means actually infinite suppressing dilation. The only way to fail is either through rotation of the wedge or failure of the wedge. And in the other extreme case, free dilation, no effective stress. That means as soon as you break the interface strength, then it has to dilate. It will dilate.
Yes. Okay, now it's more clear. I think now this story is more clear. Yeah.
Yeah.
Makes more sense to me. Yeah.
Yeah.
All right. So I'll make some changes and let you know.
Yeah.
Yeah.
I'll be working next week, at least on Monday, Tuesday.
Tuesday. Okay.
Tuesday,